Good morning, professors. I'm Leung Ik Chong Josephine from Ying Girls School, and my teammate Lei Wai Shan. Our topic today is the application of Sudoku, of graph theory to Sudoku. So this is a common 9 times 9 Sudoku. You need to fill all cells with numbers 1 to 9 such that each row, column, and block consist of numbers from 1 to 9. This is an unsolved Sudoku puzzle, while this is a solved Sudoku puzzle. How many solved Sudoku puzzles are there? This is the question that we are interested in. In fact, researchers proved that the number of Sudoku puzzles is 6.7 times 10 to the power 21 by a computer program. Therefore, we'd like to answer this question by using another approach, relating Sudoku graph to graph theory. We will divide the presentation into 3 parts. First, we will relate Sudoku to graph, expressing Sudoku as Sud_n. Second, we will find the chromatic polynomial of Sud_n, which leads to the number of possible Sudoku puzzles. Then, we will present further findings, including relationship between larger graphs and smaller graphs, and the properties of product graphs. Sudoku is closely related to graph theory, as a Sudoku puzzle can be solved by considering it as a vertex coloring problem. The assignment of colors to the vertices of a graph such that no adjacent vertices have the same color. The Sudoku graph is established by one-to-one mapping from cells to vertices and adding edges between 2 vertices if they are in the same row, column, or block. We denote the Sudoku graph by Sud_n, where n to the power 4 is the number of cells. Filling a 4 times 4 Sudoku puzzle with numbers 1 to 4 is the same as coloring the whole graph with 4 colors. In general, solving a Sudoku puzzle is the same as coloring the Sud_n graph with only n squared colors. Now we know that Sudoku can be expressed as graph Sud_n. But how does Sud_n look like? Before answering this question, we will introduce what NEPS is. The non-complete extended p-sum of graphs is a graph product operation. Here is the definition. G is the NEPS of graphs with respect to basis B. It has a vertex set that is the product of the vertex sets of starting graphs. 2 vertices are adjacent if and only if there exists an n tuple such that when xi equals yi, beta I equals 0, and when xi is adjacent to yi, beta I equals 1. For example, let graph G be the NEPS of G1 and G2 with respect to basis B. We will take vertex A1, A2 as reference. In G2, A2 is adjacent to B2. As A1 equals A2, A1 equals A1, and A2 is adjacent to B2, under the basis 0, 1, A1, A2 is adjacent to A1, B2. Common NEPS include direct sum with basis 0, 1, 1, 0, and direct product with basis 1, 1. We will use them in the next part. Sud_n is defined as the NEPS of 4 complete graphs with a certain basis. The detailed proof is provided in our report. Now we will proceed to part 2, finding the chromatic polynomial of Sud_n. Here are some definitions. Chromatic number is the least number of colors to color all vertices of a graph, such that no adjacent vertices have the same color. Chromatic polynomial is a function to count the number of different proper colorings on a graph with k colors. For complete K4, the chromatic number is 4, and the chromatic polynomial is found to be this. It is previously proved that Sudoku can be expressed as a graph Sud_n. Therefore, by finding the chromatic polynomial of Sud_n and letting k equals n squared, the total number of solved Sudoku puzzle can be found. But how can we know the chromatic polynomial of Sud_n? We can determine it by deletion-contraction property, where contraction refers to unifying vertices I and j into one vertex, and deletion is deleting edge ij from the graph. It is found that the chromatic polynomial of a graph equals the chromatic polynomial of its deletion minus the chromatic polynomial of its contraction. You may refer to the report for the proof of this theorem. Please note that the chromatic polynomial of an empty graph with n vertices is k to the power n, and that of a complete graph is this polynomial. After using the deletion contraction method for several times, any graph can be descended into null graphs or complete graphs. In this way, chromatic polynomial of a graph can be determined. For example, for the direct product of K2 and K2, which is under basis 1, 1, after a series of deletion and contraction, we can obtain null graphs only. Now we count the number of null graphs occurred and find their signs. The count refers to the number of paths G to get to the null graph, and graphs of deletion have positive sign while graphs of contraction have negative sign. Now we know the chromatic polynomial of G. Besides using deletion contraction method, we can also use Sage virtual machine to construct a graph and calculate its chromatic polynomial. However, the Sage program requires extensive power to construct the direct product of K4 and K4. Without computers that are more powerful, we cannot calculate its chromatic polynomial. As suit n is much larger than G4, its chromatic polynomial cannot be calculated. So it is impossible to find the total number of Sudoku puzzles without powerful computers. Thus, our research shifted focus to exploring the properties of closed suit nk, but not determining the chromatic polynomial of suit n itself. It is found that we can determine chromatic polynomial from lower order graphs to higher order graphs. We proved that the direct sum of Kn and Kn is a subgraph of the direct sum of Kn plus 1 and Kn plus 1. Moreover, the direct product of Kn and Kn is a subgraph of the direct product of Kn plus 1 and Kn plus 1. The proof is shown in our report. We can now obtain the chromatic polynomials of the direct graph of a large complete graph from finding the chromatic polynomials of direct sum and direct product of small complete graphs first, then using the deletion contraction property. For example, to find the chromatic polynomial of direct product of K3 and K3, calculate the chromatic polynomial of direct product of K2 and K2 first. Then use the deletion contraction method until only K2 and K2 and null graphs are left. As the total number of graphs is too huge, the result is obtained by computer programming. Graphs of deletion have +1 sign, while graphs of contraction have -1 sign. The total number of null graphs is then counted. The direct product of K2 and K2 appears in level 17, being a graph of contraction. The chromatic polynomial of the direct product of K3 and K3 is thus calculated. Thus, it is believed that the chromatic polynomial of the direct product of Kn and Kn can be deduced from the chromatic polynomial of the direct product of Kn minus 1 and Kn minus 1 theoretically. This finding greatly reduces the work of deletion contraction method. We also found some properties of product graph. This lemma suggests that when H is isomorphic to a complete graph and is a subgraph of G, the chromatic polynomial of H can divide the chromatic polynomial of G. Moreover, the chromatic polynomial of the direct product and direct sum of Kn and Kn is divisible by the chromatic polynomial of Kn. Also, the chromatic polynomials of the direct sum of Kn and Kn and the direct product of Kn and Kn are both n. Here is the outline of the proof of this theorem. First, assign a coloring scheme that proves that to shade all vertices in a systematical way. Then show the coloring scheme proves that the chromatic numbers of the direct sum of Kn and Kn is smaller or equal to n and larger or equal to n. This implies that the chromatic numbers of the direct sum of Kn and Kn equals n. To sum up, although we failed to calculate the total number of solved Sudoku puzzles due to the lack of a high-power computer, the finding of determining chromatic polynomials from product graph of lower order to higher order has a great significance in calculating chromatic polynomial of suit n. It reduces the scale of deletion contraction method. Also, the two theorems related to product graph also contributes to the calculation of chromatic polynomial of suit n. For further research, the properties of Kn times Kn times Kn times Kn can be explored, as this is the NEPS of Sudoku under a particular basis. With further research, its chromatic polynomial can be found with extensive power. And this is the end, and thank you for listening to my presentation.